which introduces the concept of space-time, the unification of space and time, and quantum mechanics, which says that the world is intrinsically probabilistic, not deterministic like in classical physics. Now, the standard formulation of quantum field theory uses the concept of fields, and for a given theory, we can, from fields, construct Lagrangians, path integrals, and from path integrals, we can calculate amplitudes using the methods of Feynman diagrams. And the Feynman diagrams is a very nice diagrammatic way how to organize the perturbative expansion, where at the leading order, we get only 3-level diagrams, while at the next to leading and higher orders, we get diagrams for loops. So the perturbative expansion here is organized as the loop expansion in Feynman diagrams. Now, quantum field theory has passed a huge number of checks in the last 70 years, and I will just show one of the most famous ones, which is magnetic dipole moment of electron. You can here define a dimensional quantity called G factor, and that was predicted by Paul Dirac in 1928 to be equal to 2, and it agreed with the experiment that time. And from the modern point of view, that would correspond to the 3-level calculation. Now, in 1947, Schwinger calculated the one-loop correction, and it was the famous alpha over 2 pi expression, and it agreed up to 4 decimal digits with the experimental value that time. Then later, people calculated a 2-loop correction and confirmed with the experiment, 3-loop correction, and today there also is a 4-loop correction, and the agreement between theory and experiment is up to 12 decimal digits, which is one of the greatest achievements in comparison of theory and experiment. However, this calculation and many other calculations rely on an important fact that the theory is weakly coupled and the perturbative expansion makes sense. But if we deal with the strongly coupled theories, we cannot use the perturbative expansion anymore, the phrase. And there are a number of approaches how to deal with strongly coupled systems. But here I want to mention one of the important surprises that happen with some strongly coupled systems is that they are dual. Not only that they are not as complicated as one might expect, but they are even dual to weakly coupled systems. And that has been seen in a number of cases in gauge-gauge dualities, where there is a strongly coupled gauge theory on one side and weakly coupled gauge theory on the other side, and they are dual. And also the famous ADS-CFT correspondence, and the strongly coupled gauge theory is dual to weakly coupled gravity theory. Now this is also one evidence that our picture of UFT, in terms of Lagrangians and Feynman diagrams, is not complete. There is also some other tensions of quantum field theory when you try to combine it with gravity, or you want to apply quantum field theory to the entire universe. So it's begging for some new understanding of field theory. But if there is such an understanding, some new picture of what the quantum field theory is, we should see its implication already at the weak coupling, where the Feynman diagrams and perturbative expansion works. And there has been an explicit evidence for that in the case of scattering amplitudes. So that's what I want to talk about. And in the early days, this evidence was seen in some unexpected simplicity of final results in comparison with with the results in intermediate steps. So let me just briefly tell something about what are the scattering amplitudes. So these are functions of spin and kinematical variables. When squared and integrated over the space, they build a cross-section, and the cross-section is measured by experimentalists at colliders. So typically there are some initial states, some particles they collide, and there are particles in the final states, and the probability or different rates of different final states are given by the cross-section. Now, the colliders can scatter different particles. They can scatter electrons, but to reach higher energies, we typically scatter protons, like at LHC. Now, the protons are not elementary particles. There are quarks and gluons inside protons, but if they are at very high energies, they become effectively free. So it makes sense to talk about the scattering amplitudes of gluons or quarks. And at very high energies, the gluonic amplitudes really dominate. So from this point of view, we can say that LHC is gluonic factory, despite there are some other important processes going on there. So from the theoretical side, it's important to know the amplitudes of gluons for very high multiplicities. So 2 gluons in the initial states and many gluons in the final states. Now the gluons have 2 different helicities, plus and minus, and the amplitude depends not only on the number of gluons involved, but also on the types of gluons, which are plus and which are minus. So this is another property that defines the amplitude, another number. Now, what was the status of the art of these calculations of gluonic amplitudes in early 80s? So the most complicated process calculated at that time was the scattering of 5 gluons. 3 gluons in the initial state and 3 gluons in the final states at the leading order, so 3-level amplitudes. And the straight calculation using Feynman diagrams gives us 24 pages of algebra like that. So this is just a straight expansion of the result. Now in 1983, US government approved a new collider, SSC, which was supposed to reach 40 eV, which would mean that there would be even more gluonic collisions and even higher demand on doing theoretical calculations for predictions. And that was the motivation to go farther, and the next amplitude on the list was 6 gluon amplitudes, 2 gluons in the initial states and 4 gluons in the final state. And that was the amplitude Stephen Park and Thomas Taylor calculated in 1985 for SSC. And this meant to calculate 220 Feynman diagrams, around 100 pages of calculations, but they used some smart notation and they compressed the final results to 14 pages. And they rushed to the publication with this great result, and the paper was published. It's called Gluonic 2 goes to 4. And it basically, there is a very short introduction, 14 pages of the results, and the conclusion in the paper. And in the conclusion of this paper, you can find, they write, we hope to obtain a simple analytic form for the answer, making our result not only an experimentalist, but also a theorist's delight. And indeed, within a year, they realized that the 14 pages can be compressed into a single line. And
URL.
For 14 pages is not the URL, but 1 line. And here I use a little bit modern notation, introduced a few years later, but the same expression can be written also using moment-time polarization. So they wrote a new paper, but in the meantime, when writing the paper, they actually realized that this expression is true for any number of gluons in external states. So for any gluonic amplitudes at 3 levels with certain polarizations. Yeah, so it's not completely generic, but for certain combinations of plus and minus helicities, they can generalize it to any 3-level amplitude. Okay, so that was the first hint of simplicity in scattering amplitude, which wasn't manifest or wasn't obvious at all at the level of Feynman diagrams. Now, what's the reason for this simplicity? So why the intermediate answers were so complicated and the final result was so simple? And the reason is the way how in quantum field theory we describe massless particles with spin. Because massless particles with spin have 2 degrees of freedom, 2 helicities, plus and minus, but they are described using polarization vectors, and they have 3 degrees of freedom. So we have to remove this 1 degree of freedom. So we have to impose the gauge symmetry. Which means that if we have 2 polarization vectors and they differ by some constant proportionality times the momentum, we have to identify that. And the Feynman diagrams are not gauge invariant. So if you do this transformation, you get a different answer. While the sum of all Feynman diagrams is gauge invariant. And there are huge cancellations between diagrams. So you can say that each Feynman diagram contains 99.999% of gauge-dependent answer, gauge-dependent part, which cancels in the sum, and only a tiny bit of the gauge-independent. in these calculations. And this is true in general. Well, the reason for this redundancy is also that the Feynman diagrams actually make the picture of interacting particles. So there are really some particles going in, then having some intermediate state, and then some particles going out. And these intermediate states are not real particles, they are virtual off-shell particles, and this is also one way how to say the reason why Feynman diagrams individually are so complicated. But Feynman diagrams make two of the important properties of the final result, the final amplitude, completely manifest. And this is the property of locality. Locality means that the particles interact point-like in the space-time. And for amplitudes, it means that the only poles in the amplitudes are of this form, 1 over p squared. So if p squared is 0, the amplitude goes to infinity. And the p is the sum of momenta, either external or in loops, also loop momenta. And if we sit on this pole, we calculate the residue of the amplitude on this pole, the amplitude must factorize. And it factorizes either into two lower point amplitudes, or if we sit on a pole that includes the loop momentum, it goes to the lower loop amplitude. So there are factorization rules for the amplitude. So this is locality and unitarity in the language of scattering amplitudes. And this is completely manifest at the level of Feynman diagrams. Now, the modern methods for calculating amplitudes that came after the Park and Taylor calculation, so use the lesson that it's important to stay gauge invariant at all times. So the gauge redundancy brings this extra complexity which is not there in the final answer. So stay gauge invariant and use physical states as the external states. Because in Feynman diagrams we use these polarization vectors for external states, but they have two polarizations, plus or minus. But the Feynman diagrams are all the same. But if we now plug for these polarization vectors that they are either plus or minus, not anything in between, the thing simplifies. So there are these two things that we should use. And in addition to these two methods, now they don't use any usual picture of fields and Lagrangians of path integrals and Feynman diagrams, as I said before, but they use these two properties, locality and unitarity of the final answer, and they exploit it to fix the amplitude. So in other words, you come up with some function, and if the function is local and unitary, then it must be the correct amplitude. And now you calculate this function in some different way, not using Feynman diagrams. But if the final result has these two properties, it must be the correct amplitude. So this is the idea. So let me mention two of the most important methods to calculate amplitudes that came after Park-Taylor calculation. And the first method are recursion relations. And it works for tree-level amplitudes. So now it's not completely general, it's only for the tree-level amplitudes. And it uses this property of unitarity, that we have only local poles, and when we sit on the pole, the function must factorize into two pieces left and right. So it uses this property together with some shifts of external momenta and using Cauchy formula. So I will not go here to the details, but basically if you take this equation as differential equation, it's integrating this equation in some abstract sense. And this is schematically what the final result look like. So the amplitude can be calculated as sum of products of lower point amplitudes. So therefore it's recursive, because you always get the product of lower point amplitudes that you already know, and then you recurse it down to the most elementary amplitudes. And this can be used in large class of theories. It's in many theories, gauge theory, gravity, and other theories. And here I show some comparison of how efficient the method is. So this is the comparison of number of Feynman diagrams in different gluonic processes against the number of terms in the recursion. You can see that comparison is quite impressive. And actually these recursion relations are now used in the leading order codes for predictions for particle accelerators. Now the second method is for loop amplitudes. It's called unitarity methods. And it's The basic equation here is then 1. It's the equation for unitarity cut, and you can obtain it by applying twice the equation coming from unitarity I showed before. And this is maybe more familiar because it looks like optical theorem. It's actually a version of optical theorem. And it means that if we take the amplitude, now the integrand of the amplitude before integration, and we sit on two poles at the same time with the same loop momenta. So in other words, we are doing the double cut of the amplitude. The amplitude splits into two pieces, left and right. And these pieces now, there are lower point and also lower loop. So we use this equation. And the way how to get the amplitude in these methods is first to generate a basis of integrals, not Feynman diagrams, just integrals, with unknown coefficients, and now apply this equation and fix the coefficients. So that's the method. So and here there is some examples. So for example, this is the basis of integrals for 4.3 loop amplitude. It's supersymmetric theories. And now you apply these conditions and you fix the coefficients in front of them. Now these methods are actually used for making experimental, to making predictions. For example, for LHC. And especially they are used in calculating the QCD background, because when searching for some beyond standard model physics at accelerators, it's very important to have the standard model prediction under control up to higher multiplicity and higher order. And these methods are used in black hat collaboration, which generated a lot of new results in next to the order one loop calculations of gluons for LHC. So this is a plot used by CMS to compare the different predictions with explicit data. So the blue is the black hat, and well, it's not. Unfortunately, the colors are not very good. But here, this is the final states of W and number of jets. The number of jets is here. And you see that the experimental and the theoretical predictions are quite good. And there is also a comparison with other methods using proton showers. Now, so this has been a great success using these methods. But the question is if there is any deeper structure here. Yeah? So we saw that we can exploit locality and unitarity in a way that doesn't use Feynman diagrams and get faster to the final result. But the question is if there is something more than that, or if this is really the only way how to think about amplitudes. And now to attack this question directly would be too complicated to, for example, jump directly to QCD amplitudes. So there is a time-proven method how to make progress, and that's first to concentrate on the toy model. So we want to search for some toy model where the results will be simpler, but then the methods that we find there we can actually then also extend to other theories. And we have a wish list, we have high demands on what the toy model is because we want to pick the good toy model. So we want a 4-dimensional interacting theory. So it must be in 4 dimensions and be fully interacting. We want that to be close to the real world, meaning QCD, in this case, as much as possible. And the other thing is that we want to generate as many explicit results as possible, and any new idea, we should be able to falsify immediately any new idea which comes with some predictions. Yeah? So also many explicit results. And this is our toy model. It's called maximally supersymmetric animals theory in planar limits. So I will just refer to it as toy model. It's not important much to know more details about it. The important thing is that this theory is conformal, so it doesn't have any UV. The UV properties are trivial in this theory. And in addition, the perturbative series here is convergent. So it's not asymptotic series, like in most of the cases, but actually convergent series. There are no non-perturbative effects in this theory. But it's a great toy model for QCD for a number of reasons. And the main reason is that the tree-level amplitudes in this theory are identical to QCD tree-level amplitudes. So for gluons, it's just direct correspondence, and for other QCD amplitudes, including quartz, it's kind of non-trivial, but you can extract all tree-level amplitudes in QCD from this theory. The loop amplitudes are simpler, The IR structure is similar, but not the same. And there is no confinement. So the theory is clearly simpler than QCD. However, in the past, it was actually a very useful theory to explore some new methods. And the two methods I showed before, the unitarity methods and recursion relations, originated in this theory. So people found these methods in this theory first, and then extended to QCD and other theories. So it was already useful in the past. Well, in addition, this theory actually is also a very useful playground for many other ideas using different approaches, including integrability, because this theory has infinite dimensional Youngian symmetry. So people doing integrability try to solve these amplitudes in this theory using integrability, despite they can solve something, but amplitudes still seem to be too hard to calculate directly. And it also plays an important role in ADS-CFT correspondence on the CFT side. And there are also some interesting calculations in this theory at strong coupling using ADS-CFT, calculating some Wilson loops in ADS. And there are also some other approaches. I will not go into details here. So it's a useful theory to start with if you want to explore some new ideas. For us, the important aspect of this theory is that the amplitudes are simple, or simpler than you would expect. So that gives a hope that we can actually see some structure in the amplitudes. And here is the comparison of 4-point amplitudes at one loop and two loop using Feynman diagrams and using unitarity methods. That actually, this calculation was done a long time ago. And you can see that the number of Feynman diagrams at one loop is 87 versus one diagram. If you compress everything using unitarity methods. And at two loop, it's around 1,000 Feynman diagrams versus two integrals on the other side. So the amplitudes are simple, which makes our life easier when analyzing and trying to see some further structure in there. So the main question here is, what is the amplitude? Or does it exist some new definition for what the amplitude is? The standard formulation of quantum field theory, even using these modern techniques, would say that the amplitude is a function which is consistent with properties of locality and unitarity. So that's what I said before. So if you come up with a function which satisfies these two properties, you have the correct answer. And you don't have to worry about how you actually calculate it. Yeah, it's the correct answer. But our goal is to find some different definition of the amplitude in this theory. And we don't want to use any fields, Lagrangian of path integrals, but that was also already one of the features of these methods I spoke before. But in addition, we even don't want to use any unitarity or locality. So these will be not our guiding principles. We want to see these principles to be emergent from some other properties, some other underlying principles. And we also want this new formulation to be useful for calculations, so to actually be able to generate some new results. Okay, so let me tell you a little bit about the historic prelude, what happened before the final picture was found. And everything started with observation by Andrew Hodges in 2009. So he did some particular calculation of some amplitude, 2 goes to 5, at 3 level. And he used his new variables called momentum twister variables. So he defined some new variables. And he did the calculation of scattering amplitudes, and he used the recursion relations, 3-level recursion relations that I showed before. And he did a calculation one way, and he got 2 terms. And now in this, using these variables, he was able to interpret these 2 terms as volumes of tetrahedra. Then he did the calculation using different way, and he was able to interpret it, the 3 terms that he got in the result, as the volumes of another tetrahedron, 3 tetrahedra. And then he saw that if he glues them together, they actually build this polyhedron. So this is the amplitude. This is just different ways how to triangulate the amplitude into pieces. So this is the full amplitude, and well, this is actually directly the full 3-level amplitude of gluons. Because we are at the 3 levels, so QCD and this theory give the same answers. So the amplitude was a volume of this polyhedron. Then together with Andrew, we actually found some larger class of amplitudes that basically all three-level amplitudes, but again, just for some special helicity configuration, not the ones considered by Park-Taylor, to some other one. And again, the amplitude was always some volume of some polyhedron. So, so there was some evidence, or this was an evidence, that in certain cases you can think about the amplitude as volume. But that was all three-level, and not even for all three-level amplitudes, some of them. But it was first evidence for some new structure. There was the second evidence that amplitudes have something to do with Grassmannians. Grassmannians are some basic objects in algebraic geometry. Roughly speaking, it's a way how to describe a plane in higher dimensional space. So it's a configuration of k-planes in n dimensions. And there was some formula, some kind of magic formula found by these people, showing that this simple object contains some of the all-loop information about the amplitude. Not the amplitude itself, but some all-loop order information. Okay, so based on these two observations, we made a weight conjecture that the amplitudes in this theory are volumes of some regions in some space. So that's a very vague conjecture. But now we actually know what these some regions and these some space are. So we can actually now make a precise conjecture and prove it. And this leads to the concept of Amplituhedron. So let me just outline the strategy, how to find the final picture. And that's to start with some simple intuitive ideas. Simple intuitive geometric ideas, and describe them using equations. And then generalize. So consider some more complicated geometry and higher dimensional space. And use the same equation in the end, where the intuition is gone, but the same equation persists. And the simple intuitive geometric picture is describing a point inside a polygon. Now, if we consider all points inside a polygon, then we can talk about the interior of the polygon and about the area of the polygon or the volume of the polygon. Now we generalize in two different directions. And this is just like the schematic way how to get the object. So I will not give the proper definition, schematic way. So first we generalize to higher dimensions. So we are going from polygon to polyhedron and to higher dimensional space. And in the other direction, we consider the point, then instead of that we consider a line, then a plane, and the higher dimensional plane, and then the higher dimensional plane and bunch of lines. So this is the more complicated geometry direction. And then unification of these two directions gives the definition, or a little simplified definition of the Amplituhedron, which name just points out that there will be some connection with amplitudes and with polyhedron. And it's labeled by three numbers, n, k, and l. And roughly speaking, it's a k-dimensional plane with l lines inside k plus 4-dimensional convex space defined by n vertices. So, okay, so this is what the object is. The details are not so important. The important thing is that it's labeled by three numbers, n, k, and l. And also this picture that I showed before, it's not completely a random picture for high dimensional space. So it was made by artists who started with this polyhedron and drew these colors around it. So this is the way how to make high dimensional picture from three-dimensional. Okay, but what is the relation to amplitudes? So the volume of this space is the scattering amplitude. So in particular, the volume of this space gives the integrand of amplitude, the maximally supersymmetric Yang-Mills theory in planar limit. This is our toy model. When the n corresponds to the number of particles, k carries some helicity information, and l is number of loops. And for l equals 0, these are three-level amplitudes, and these are three-level amplitudes directly of QCD gluons. So this is a good conjecture, but how we actually prove it, or give some evidence for it, and that's exactly the check of locality and unitarity. So we can show that whatever results we get as a volume of this space it will have these two properties. The only poles in this expression will be the local poles, and on these poles, the expression for the volume will factorize. And we can also check, because there are lots of explicit reference data generated by other people in the last number of years, we can also check that this picture gives the agreement with the reference data.
So just going back one slide.
Yes.
The list of numbers, you have N, K, and L.
Yes.
So N and K are sort of physical things, right?
Yes.
Number of particles to list.
Yes.
Whereas the number of loops is more, I would think of it's something, a technique that you're using to
Right,
calculate.
but we still use perturbative expansion here. Yeah, so this is a perturbative object, so the function we get is the integrand for the amplitude.
Yeah.
So it is the loop momentum in it. Yeah.
But the question. At the end of the day, I'm meant to sum over the number of loops.
Right.
So is there a bigger geometric structure that appears when you do that sum?
Yeah, so that's a very good question. So we know what this object is at any given loop order. It would be great to sum it, to give some non-perturbative, just full expansion for that. We don't know what it is yet. But it's a great question. Yeah. And especially because we have under control all the pieces,
Right.
at least at this geometric language, then it's an actual question to do. Yeah. We don't know how to do it.
So you get on the real?
Huh? Yes.
So do you get on the real numbers?
Yes. So you mean if the things are real here?
So this
Sorry.
so amplitudes can be complex numbers. So you get on the real numbers.
Yeah. So this is for real. Yeah. So we get real numbers for volumes. You mean?
Yeah.
Yeah. Yeah. So yeah. So there are some important details here because the volumes are real, of course, and even positive. The momenta, there is some, so it's some, we inject some external momenta which correspond to the configuration that gives the real volume. So there are some details about the real and complex, some distinction between that. Yeah. So I will not talk about it, but yes, the volumes are real, so we get real numbers out of it.
Yeah, how do you know what field, say, it is for maximal symmetric Yao-Liaos? Say if you draw this, how do you know that is that?
Yeah, so why this picture corresponds to this theory and not the other one?
Right.
Yeah. Well, first you might naively think it doesn't correspond to any amplitude. Yeah. Why this picture should correspond to anything?
It's nice
So,
to have locality and unitarity, right? But
yeah. So the thing that why it corresponds to the to amplitude in this theory is still a bit hidden on the next slide, and this is what I really mean by the volume. Because I just said volume, I didn't say what I mean really by that. And the volume here is some differential form. And the thing is that the form, the definition of the form is chosen such that it exactly mimics the type of singularities which show up in the amplitudes in this theory. This is called logarithmic singularities. But so basically it means that the object is given by some set of inequalities. This is how the object is defined, for example, from a definition. And if we want to calculate its volume, we write some differential form for it. So I just give here some simple examples. So suppose that we have just one-dimensional version of that. X is bigger than 0. So this is some one-dimensional space. Then the volume of that would be dx over x. The volume is defined such that the poles there are simple poles on the boundaries of this space. So x is equal to 0, the volume is just that. For the two-dimensional space where y is bigger than 0 and x is bigger than 0, it's just dx over x, dy over y. And then we can have some little more complicated versions. Y is bigger than x and bigger than 0, where the ranges for y depend also on x. And the volume is dx over x, dy over y minus x. So this is not
integrating eventually, or
yeah. So this gives the integrand.
this gives the
Yeah. So if we want the final answer, then we would have to integrate. Yeah. So therefore, this gives a differential form. Yeah. So
there's overlap between these two cases, right?
this is just examples. Yeah. These are actually not the ones which are relevant for the final picture. I just wanted to show what I mean by volume here. Now, so now I will show you. So this generalizes to the cases we care about. So now I will show you that in some special case of 4-point scattering, when you have two gluons in initial states and two gluons in final state, these inequalities that define the space actually can be very nicely interpreted as finding the configurations of vectors on a plane. And because this problem is extremely easy to state, but presumably extremely hard to solve, we initially called it a high school problem because we hope that we can explain it to a high school student and he might solve it. But after 2 years, we don't think so anymore. But I will just use the name that we gave to this problem.
You should give it to Davis High School students.
Davis High School student. So let me say what the problem is. So if you solve this problem, you find the 4-point scattering in this theory to all loop orders. So the exact formula. So we start with the plane and consider the positive quadrant. And now we consider the red and the blue vectors that are in this plane. And now we allow these vectors to span the entire positive quadrant, and we take the volume of this configuration. We basically say that these x, y, z, and w can go from 0 to infinity. Now the volume of that is just 4 copies of what I showed before, and if you do some trivial change of variables, you actually see that you get a 1-loop amplitude in this theory. Now consider two vectors. We don't say anything else, so there are two pairs of vectors, two blue and two red. If we don't say anything else, we again allow these vectors to span the entire positive quadrant. The volume of that is just square of the volume that we got before. And we get this, this expression, and it actually corresponds just to the 1-loop amplitude square. Yeah, because it was just square of the problem before. But now, we can impose a condition, which is that if we take the difference of the two blue vectors and difference between two red vectors as vectors, they meet at some angle, and the angle must be bigger than 90 degrees. So in this case, actually, it's smaller. So this will be not allowed configuration. And now we find all the configurations of vectors that satisfy this condition. And in this case, actually, it splits into 8 different regions. We can easily calculate the volume of each of the regions. And if we sum these 8 regions, we get this expression, which is kind of little non-trivial. So it has the piece that was there already before, and there is some non-trivial combination of these vectors. Now, if we change variables trivially, we find that this is a 2-loop amplitude. In this case, we can actually calculate these amplitudes directly using unitarity methods. But you can see that this will actually generalize. So we can consider 3 pairs of vectors and find the configurations that satisfy these inequalities, which is just pairwise inequalities of what I showed before. And the volume of this space of these configurations give the 3-loop amplitude directly. So there is now no expansion in terms of diagrams, no fixing coefficients, it's just directly the amplitude. And now this is the general case. So we have L red vectors, L blue vectors, pairwise satisfying these conditions. And if we find the configurations of all these vectors that satisfy these conditions, we find the L loop amplitude. And here actually, well, for generic amplitude, we don't have any other method how to find it. Or there is no general method how to do it, because using unitarity, you would have to generate some loop diagrams at random loop order, but that's something which is not solved even in the graph theory how to do it. Okay, so this was an example how you can map the definition of Amplituhedron to some concrete problem of finding vectors in a plane. So now let me go a little...
So say it's equal, you mean after doing the integral?
Well, this is the integrand. Yeah, so it's the integrand. Yeah. So you would...
But then you integrate it, and
if
then
you want to
get the
integrate...
loop or whatever the amplitude.
Well, here, for example, these pictures are also pictures for integrand. Yeah, so if you want to integrate, yeah, you would have to then integrate over the loop momentum, over the velocity. Yeah, so this gives the integrand.
It's always in a two-dimensional plane.
Yeah, it's always a two-dimensional plane. So that's the problem is very easy to state to any loop order, but I expect that it's not so easy to solve an what we hoped a year ago. Yeah.
But in this construction, there is no reference to the momentum, right?
Yeah, so let me be really more precise. So the x and y, z and w, you can, there is some easy linear transformation from them to loop momenta. Yeah, so that actually you know to all the borders because it doesn't depend on the loop order. Yeah, so it's just change of variables from these 4 variables to 4 components of the loop momenta.
Where are the external momenta?
Yeah, so here actually in this case the external momenta for the 4-point scattering. The dependence, yeah, well, okay. So the external momenta are also hidden here because if we solve for x, y, z, and w, it will depend on the loop momenta and the external momenta. Yeah, so both of them. But kind of the dependence on the external momenta here is quite easy for this scattering. Also for the reasons of the symmetry in this theory. But the external and loop momenta are both all hidden in these variables. So let me now go a little deeper into the mathematical structures that actually arise here. So I showed some example, but in general, this is the full definition of Amplituhedron. It fits on one slide. And if we zoom on this slide, we actually see some equation saying that y equals c dot 0. I will say something about this equation. The y is the Amplituhedron space, and the c and z are 2 matrices, and these are positive matrices. By that I mean that the minors of these matrices are positive. So these matrices have just real numbers in it, and they satisfy this condition that the minors are positive. Now the precise combination which minors are positive depends on which Amplituhedron we consider. But now the positivity is actually the crucial property of this geometry, and everything can be derived from it. So the locality, unitarity, and even planarity can be derived from this equation. And even the Youngian symmetries manifest from positivity. Now the question for mathematicians is, our question is, how to make these big positive matrices, how to construct a matrix which has positive minors. Because this is what we need in the definition of Amplituhedron. Unfortunately, this was solved for the 3-level case, L equals 0, by Postnikov in 2006. So he found a way how to generate arbitrary big matrix with positive minors. And this leads to the positive Grassmannian. So the positive Grassmannian is just K by N matrix, modulo GLK, where all the minors are positive. And his way how to do it is actually very intuitive. So he starts with some small matrices, which are positive. So the small matrices 1 by 3 and 2 by 3. And he attaches some pictures to them. So some blue vertex and some blue, white vertex and the blue vertex. And now he glues them together. Gluing together, so there is some well-defined procedure how to glue them together in terms of matrices, making from small matrices the big matrices such that this positivity property is preserved. And then he gets some graphs, like these ones, which are associated with these big positive matrices. And these big positive matrices are exactly triangulations of our Amplituhedron, the 3-level amplitude. So he solved this problem for us. Now, these matrices are interesting for mathematicians for many other reasons. For example, the basis of these matrices, I think the irreducible part of the matrices, can be labeled by permutations. So the basic rule here is that you take the graph, which is associated with the matrix, and you start from some external line, and you go through the diagram, then you turn left on the white vertex and right on the blue vertex until you hit some other number, and this procedure always generates a permutation. This is a permutation for this diagram. And then you can also combine it into something called the Lean table, which was found by famous mathematicians Pierre Lean, from which you can also say some different properties. The amusing feature here is that the permutations and these diagrams are actually closely related to the juggling patterns, which is not so crazy because if you juggle many balls, you throw them into the air and you want them not to fall at the same time to your hands. So you set with some initial permutations and you want them to fall in some different permutation. And actually one of the mathematicians studying the positive Grassmannian and the relation to permutation, Alan Knudsen, professor at Cornell, held as a student at Caltech the world record in juggling. So he could do 12 balls at a time. And he even wrote a paper on relation between positive Grassmannian.
While he was juggling?
Huh?
Well, did you write the paper while he was juggling?
Yeah, he's still very good in juggling. I don't think that he can do 12 balls anymore. But. And these graphs actually appear also in other places in the math literature, so they are related to cluster variables. When you associate some variables to faces or edges on of the diagrams, and they satisfy some cluster transformations. And also the dual graphs for these graphs, when you write the vertices in faces, and instead of face you actually write vertex, so do you dualize corresponds to quivers. There is a nice interpretation of cyberduality here. And this is also useful to solve the problem of shallow water waves and KP equation. So here is the picture of some water waves. So the idea here is that you have these waves, solitons on the boundary, and you let them scatter in the middle, in the bulk, and they form these type of diagrams. So they can, whatever can happen with these waves can be classified using the same diagrams. But for us, the importance of these diagrams is very different. And that is that we can think about these diagrams as on-shelf physical processes. Yeah? So there was some big positive metrics associated with each diagram, and the volume of it was the piece in the triangulation of Amplituhedron, but we can calculate the same piece by taking the product of 3-point amplitudes, then the blue and white vertices we associate with 3-point amplitudes. So there is a very radically different interpretation of the same diagrams as physical on-shelf processes. Because here, this is not Feynman diagrams, these are diagrams where all legs, both internal and external, are on-shelf. And this is, the connection is actually extremely rich, and we wrote a long paper on it, also with mathematicians, Goncharov and Kosnikov, and it has 158 pages, and we have a lot of figures in the paper. I don't know if this is the record on archive, it's 264 figures. So, let me here say that there is this interesting comparison between having Feynman diagrams as some processive scattering of elementary particles in 4 dimensions, so the picture of interactions in 4 dimensions, and some higher dimensional static object, which is our Amplituhedron. So this is an interesting comparison of how to describe scattering amplitudes, either by dynamics in 4 dimensions or some static situation in higher dimensions. And actually this is the connection between amplitudes and this type of mathematics I showed you. It's kind of interesting because these subjects have never interacted so far. Predictions of amplitudes and combinatorics, algebraic geometry, and cluster algebras, and it has been very fruitful interaction between these 2 fields. And we also have already the workshops on this subject. So in December, I co-organized the workshop at Caltech on Grassmannians scattering amplitudes, and we had more than 60 participants. There will be another workshop organized now by mathematicians in Montreal in the summer. But now let me finish, or before I finish, let me go back to the point where we started, and that's the Park-Taylor formula. So let me just show what happened with this calculation after we left it in 1985. So let's consider the same 3-level process. 2 gluons go to arbitrary number of gluons. And now we consider it in the context of our toy model. And the 3-level amplitude is the same here and in QCD. So the Park-Taylor calculation holds also for our toy model. And in fact, the 3-level amplitude can be factored out from the perturbative expansion, so the Park-Taylor really calculated this one piece. Now, in 1994, using unitarity methods, people calculated the full one-loop correction. And that was the first success of unitarity methods, and is a sum over a single type of diagram. Now, the 2-loop calculation was only done in 2009, so it took 15 years to do the complete 2-loop calculation. And it's 11 pages of results. Which is still kind of impressive because you might expect that there doesn't exist any closed form for any number of gluons in external states. But it's 11 pages, so the question is, what happens next. So is it the end of simplicity here at this point? But then we look at this calculation or at this process, and using this type of geometrical ideas that I showed before, they even predated the Amplituhedron. We found that it shrinks on a single line as a sum of a single object. And then we also added the free loop, which is the sum of two objects. So it shows that these methods are actually also powerful in getting the simple formulas directly. And there is a simplicity here. So there is simplicity at amplitudes even at high proportions. So let me now conclude. This is my final slide. So today I talked about the Amplituhedron, which is a new geometric picture for amplitudes in planar n equals 4 superdiagonals theory. And the crucial property here is the positivity in geometry, and that replaces the physical concepts like locality and unitarity. In the next step, we definitely want to look at the non-planar amplitudes, gravity amplitudes, string amplitudes, and especially QCD to see how these geometric ideas actually extend. We have an evidence that they do extend beyond this toy model. And the first evidence is that these on-shell diagrams, these pictures actually exist. You can draw non-planar diagrams, they exist in QCD. So these building blocks for the Amplituhedron exist. We still don't understand what the picture, the final picture is, how to build from these building blocks the amplitude itself. And then there is also, we have some parallel Amplituhedron type construction beyond the planar limit, which goes from some different direction. And there is also some interesting connection to effective field theories, scalar effective field theories. And the theories that seem special from this point of view are the ones that actually have been studied in very different contexts, in modified gravity and string theory, like BBI or Galileo. And here, instead of gauge invariant, the importance is in the soft limits. So we will see how far it goes. Thank you.
Let's just go back one
Yes.
slide.
Here.
In what sense are those diagrams supposed to be non-planar that we're looking at?
This is non-planar. This is planar. This is non-planar. This is planar, but has some arrows on it, and that's exactly what we have to do in QCD. Yeah, so we have to decorate these diagrams with some extra structure. Because in these supersymmetric theories, if you have an amplitude, it doesn't matter what are the helicities of the particles. All the helicity amplitudes are actually combined into the super amplitude. But in QCD, we have to distinguish between plus and minus helicity. So therefore, these diagrams are decorated. And this one is not planar.
Yes.
So, is there a conceptual reason why planar QCD would be unitary? I mean, maybe this is some background question.
Well, you ask about the perturbative expansion, if there is something missing in planar QCD. Well, there is the unitarity like loop by loop order, just to be satisfied, like this cut equation I showed before. So that would be true loop by loop order. But there is definitely, even for planar QCD, there are some non-perturbative effects. So the result wouldn't be complete. It's not the same as this. The perturbative expansion in this theory is complete. There are no non-perturbative effects, unlike in planar QCD, where in order to get the fully consistent answer, you have to add the non-perturbative effects.
Probably said it, but how did you get from the supersymmetric case to the non-supersymmetric case?
For the tree-level amplitudes.
Yeah, for the tree level.
Yeah, no, well, it's just, yes, so it's just an observation that if you calculate the gluonic amplitudes in the QCD case and in the supersymmetric case, and now in the supersymmetric case, you just set the helicities for external gluons, then the Feynman diagrams are identical. And the reason is that the matter fields are always in the vertices are in pairs. So the tree-level amplitudes actually don't have any matter fields there. And therefore, the diagrams are identical, and that's not true at loop level. Now they will be different. Yeah? And, well, actually, the correspondence between QCD and this theory is more than just gluonic amplitudes using some, but this is like more detailed. Using some tricks, you can see that all QCD amplitudes are hidden as linear combinations of some particular amplitude, these super amplitudes, when you expand the superfields.
Question?
Yes.
So sorry if this is a dumb question, but it's hard for me to understand like how much. So let me give an example. If you carried out one of these calculations and that corresponds to a calculation we haven't done yet, would you be able to trust that calculation at this point? Or do you do the calculations and see that they get the answer that we already have, and then say, something's working here?
Yeah, but many of the calculations I showed actually haven't been done. Yeah. So for example, this free loop calculation hasn't been done before, yeah, and many other. Well, the thing is that so we are in a very good position here because we have consistency checks, which are so strong that if they are satisfied, there is no other way, there is no other function which satisfies them other than the amplitude. Yeah? So this is the question: what happens in general quantum field theory? Are we always in such a good position that just the consistency checks actually determine the answer completely? I don't know. I hope this is the case, but I don't know. In this case, it is true. Yeah.
Actually, I could imagine hoping for something different, which is that you're discovering something much more fundamental than quantum field theory. And then you find the place where it actually differs and test it and find out you're right.
Maybe.
Is that even better?
Yeah, perhaps. Yeah.
But you're saying that you can be certain that your answer is unique.
Yeah.
Based upon what? An implicity property?
Yeah, so it's exactly these conditions of locality and unitarity. It's, well, one part of it is that there doesn't, basically if you already, I give you the amplitude, and now you check that these conditions are satisfied, okay? Now, there doesn't exist any piece you can add to it that doesn't violate them. Yeah. So basically, well, in other words, it means that there doesn't exist any contact terms. Yeah. It's like in effective field theory, you have the contact terms that you can add, and these contact terms don't have any poles, so they don't factorize on the poles. So these wouldn't be detectable. But here, there are no contact terms. There are no contact terms. So whatever you add, you introduce new poles in the answer, new factorization channels, and because you already matched everything using your answers or your proposal, you would basically damage these properties. Yeah. So the answer is actually fixed just by these properties here, and it's like kinematically fixed. You cannot write kinematically anything. There is actually one puzzling thing you might. This is not true only in Young-Mills; it's also true in gravity. But both in gravity and Young-Mills, you would think like, what happens, for example, in gravity it's even worse. What happens if you start with Einstein gravity and write the Feynman diagrams? You have infinite number of contact terms, because it's nonlinear, and you have, if you go to endpoint amplitude, you have endpoint contact terms. So what happens with that? How is it possible? You have a contact term here, but here the contact terms are fixed by the gauge invariance. Yeah? So it's the gauge invariance that tells you that you cannot write some random thing. Yeah. Yeah. Yes.
So following up on the last couple of questions,
yeah.
So is it a mathematical theorem that the answer you get from the Amplituhedron volume computation would be the same as from the Feynman diagram extension? And in this toy model, I mean.
Well, in this toy model, we can, well, it's like physics proof, yeah, I'm going to say, because we don't have, yeah, so it's this, it's this property of locality and unitarity. So it's really a statement about rational functions. You have a rational function, how do you describe the rational function? And you describe it using its poles. So I give you the list of residues of rational function on its poles, and that's enough to fix the function completely.
Why isn't the math proofs as well?
Well, the thing is, we tried to pursue Goncharov that we have a proof, but he told us that we don't have a proof for existence of such a thing. Yeah. So I give you, I can outline the geometry. Well, I give you the geometry, and I say that the volume of that, the precise definition of volume is a form with logarithmic singularities on the boundaries of this space. Okay. So that's what I mean by volume. And, well, maybe it is already a proof if I say that, but there was something that how do you know that the volume form exists? Yeah.
Okay, so there are some subtle points.
Yeah, there are some
that
subtle
only
things.
interest people like me. And,
We didn't have an existence proof. Once it exists, it's unique, but
Okay.
we didn't prove that it exists. Yeah.
Physicists are usually not so interested in proving existence.
Yeah. So therefore, I don't claim that we have the precise mathematical proof. Yeah.
So I want to go back to a question that was asked earlier,
Yeah.
but maybe rephrase it a little bit. Suppose that I didn't know about Feynman diagrams and somehow came up with this Amplituhedron and started looking at its properties and said, oh, look, I mean, suppose I didn't derive it from Feynman diagrams, I came up with it from some different reason, and then noticed that it was matching maximally supersymmetric planar Yang-Mills. The question that I would ask is, how did I put into this geometric structure the fact that it was Yang-Mills and not gravity or not a scalar field theory? How did I put into the geometric structure that it was supersymmetric? Is there a way of answering that? Is there a way of saying, looking at the geometry and saying directly, this is why it has this field content and not different field content?
Well, that's a hard question. Even if you don't know Feynman diagrams, you would have to tell me what are the properties of amplitudes in this theory. Yeah, so the Feynman diagrams make some of these properties manifest, some of them not.
Yeah.
But you have to tell me what are the properties. So if I have to give you the amplitude, what is the singularities of the amplitude? What are the symmetries of the amplitude? So if I have this list, then I can check it against this geometry. So that's the first thing. I would have to know what specifies the amplitude, even if I don't have Feynman diagrams.
But I'm asking
But you can ask the opposite question.
Yeah.
Well, that's I don't know. There is definitely a link between the geometry and the properties of the amplitude, and that one thing I said. These are the logarithmic singularities because it's not obvious from any other point of view, but the singularities in this theory exactly have this logarithmic character. But otherwise, no, I don't know how I would say that. Yeah, and the reason is that the standard quantum field theory properties are here completely hidden in this geometric structure. And if you want to de-entangle what is locality, what is unitarity, what is planarity, what is this property, coming from this positivity, I just briefly said that there are some positive matrices, you would have very hard time to do it. Yeah, here it's packaged in a completely different way. So,
okay, but maybe another way of asking this is to ask how rigid is this structure? Because presumably you would like to say that there are things like this
Right.
that correspond to all sorts of other
Yes.
field theories, but the way you described it made it seem like such a simple structure that it wasn't obvious that it could be deformed
Right.
at
Right.
all.
Yeah, so right. So there are a number of things, because this is really the simplest structure from this point of view you can consider, but I made I made these choices for this simplification. So I said that the singularities are only of that type. This is true in this theory, this is not true in QCD. So for example, if I want to do QCD and build this type of object, I would have to say that there are singularities of that type and this type. So I would have to make this assumption about how to define volume, in a different way.
Okay.
That's the first thing. The other thing is the geometry itself. Perhaps there is some richer geometry that I have to consider. I consider kind of the minimal thing that fitted the amplitude picture. But QCD is richer. I would have to say something about helicities. I would have to introduce some orientations on that or something like that. Yeah. So there are many choices you can make beyond that. Yeah. Fortunately, in this theory, the picture was so crystal clear that we were able to fit it to this simple geometry. But going beyond, there are several levels where you can try to extend it. Yeah. And
I'd like to just make a suggestion, which is that I think some people are still interested in asking questions, but I'm suspecting not everyone, so I'm suggesting let's thank our speaker, and people who want to stay and ask questions, let's stay, but let's let other people leave. Okay?